Hi, my name's Michael and welcome to my channel, Logic Foundry. The computers that we use today are built upon decades of designs, decisions and abstractions. Their inherent complexity makes it really hard to understand what's happening under the hood and at the very lowest layers. As a software engineer by trade, I am all too familiar with the fact that I am standing on top of the shoulders of giants with every piece of software that I build. Well, there's nothing quite like building something yourself for understanding how it works. Join me on my journey to build a computer from scratch, and we'll figure out how this works together. At their lowest level, chips are composed from trillions of transistors. The transistors are arranged into circuits within the chip and are what makes computations possible. Transistors can be arranged to form logic gates, which allow for various input signals to be combined to produce specific output values. Let's cover some of the most common gates that we see in the real world. To start with, we have the NOT gate. The NOT gate takes some signal and outputs the inverse of the signal. So in this case, given that we're dealing with binary, if we have a signal of 1 come in, we'll get a signal of 0 coming out. Next, we have the AND gate. The AND gate will only be active or emit a 1 if both of the inputs are 1. Any other signal will result in it outputting a 0. Then we have the OR gate. The OR gate will emit a 1 if either of the inputs are 1, or if both of the inputs are 1. And then we have the exclusive OR gate. And the exclusive OR gate, which can be differentiated from the OR gate by this extra line on the input, will only emit a 1 or an active signal if one of the gates are active, but if both are active, it'll output a 0. You can effectively think of a logic gate as a pure function. They produce some fixed output given some input. To help explain the relationship between the output of a gate given its inputs, we can use a truth table. A truth table records all the permutations of their inputs to the gate and their associated output. So for example, here I have two different sized input. Here I have two differently sized truth tables, one for the single input NOT gate and one for the double input AND, OR and XOR gates. Filling these truth tables out, we have an output of 0 for a NOT gate if the input is 1 and an output of 1 if the input is 0. Now these become much more useful when we have more complicated gates or more complicated circuits composed from several gates for understanding the relationship between the inputs and the outputs. But to fill out this table here for the AND gate, we described earlier that it will only output a 1 if both of the inputs are 1, otherwise you just get 0 as the output. For the OR gate, we described that the output will be 1 if either of the inputs are 1 or both the inputs are 1. And last but not least, for the exclusive OR gate, the output is 1 if either of the inputs are 1, but not both. If both are 1, then we emit a 0. So let's combine these into a more complicated example. Let's say I had two AND gates feeding into a single exclusive OR gate. What would the output be? Well, in order to compute this, I'm going to need a slightly more complicated truth table. In this case, this means that I actually have 4 inputs and 1 output. Let's just put these all over here. And we'll go and get all of the inputs that we're going to be using. And so you'll notice that as we add more and more gates, that the number of combinations increases, and therefore the complexity of what we can model increases as we add more and more gates to our circuit. Now we won't go and enumerate absolutely all of them, because that becomes pretty tedious. But let's at least go and do the first few. So in here, let's say that we have all zeros into our gate. What are we going to get out of here? We're going to get a 0. We'll get a 0. Since neither are active, the exclusive OR is also inactive, and so therefore we get a 0. Likewise, if we've got all zeros except for 1, then we also have a 0 as the output. Same goes for that. But what if we have 2 inputs coming in here, and these are 1? Then this becomes 1, and the output is 1. Let's just go through a few more down here. If we have, we're going to have 0 for all of these. If we have a 0 and a 1 in one of the gates, we still get a 0 here. 0, 1, 0, 1. So if 1 is coming into each of these, but we're still getting zeros, we're still going to be getting zeros out of the AND gates, and that then locks to 0. Likewise, the same here. We have 1 coming into both of these, it's still going to be 0 as the output. But down here, we start getting 1 as the input. And so you can see this is how we can effectively take a more complicated set of or arrangement of gates, as we've got here, and derive what we expect the outputs to be given the inputs into the circuit. Also, you can see, even just with 4 inputs, there's a lot of different combinations that we have here. These logic gates can be composed with state to build up powerful processing devices. Now, for the purposes of our experiment, we're not going to go quite as low level as building it up directly from gates. Whilst it'd be interesting, it'd be really time consuming and would mean that we wouldn't be able to get into other interesting areas of how computers work. Instead, we're going to make use of a device called an FPGA. FPGAs can be configured to represent pretty much any digital logic circuit that you can think of. So I'm going to be using a board called the RTA7, which has on it the Arctix 7 FPGA from Xilinx on it. In my next video, I'm going to explore how we can build up combinatorial circuits from logic gates on top of an FPGA.